Okay, in Gantt chart, we have to put P4 first for 3 units and P4 is executed 3 units or 3 nanoseconds, then it is finished according to the round robin algorithm. But because of its burst time is 8, it has 5 more nanoseconds for execution. So we have to put it back to the memory. But at that time, when time is 3, there are 3 more processes already there. P1, P5, when time is 1, P3, when time is 2, and P1, when time is 3. Okay, so while we put the P4, we will put it after these 3 processes. And remaining execution time of P4 is 5. I am writing here because for this one, this 3, I know it is written here. But for this one, not to confuse, I am writing just like this, not to forget. Okay, so also the order of execution is clear here when I did this. I know the next process is P5. How much time? Again, 3 nanoseconds, because my time quantum is 3 units. So time will be 6. P5 is burst time is 5 nanoseconds. So when I finish it here, okay, I will put it back again because I have 2 more nanoseconds to execute. But I have to check when time is 5, which processes are already in the memory? When time is 6, because it will be P5 will be after that. So we put all 4 processes, only process 2 remains, which its arrival time is 5. So before P5 is executed, P2 is arrived here. P2. So I will put P2 here, and then I will put P5 here. How much time is left? 5 minus 2, 3, 2 nanoseconds. So the main thing is when we execute one process, and this is happening in the beginning. Now we don't need to think about the which memory is already in the which process is already in the memory, because all processes are in main memory now. So we don't need to think this order more. But till here, this is the tricky part of this algorithm. Is it clear or not? I am not getting an answer, but I don't know if it is okay or not.
It's okay.
Okay. I'm also recording the lecture, so you can check it again. Which process will be executed next?
process 3.
Yes, process 3, because all the processes are here, and this is the order of execution. I wrote from left to right, so it is starting from this direction and goes to right. So the next one is process 3, P3. So it is always 3 nanoseconds. If the execution time is not less than 3 nanoseconds, it is always 3 nanoseconds, the execution time. Because we set like that, 3 units. If I say 4 units, you have to make each of them 4. P3, 3 nanoseconds. What is the burst time? 6. So when PT is finished here, I don't need to think about if any other processes came to the memory, because all of them are there. So I can directly put P3 here, and how much time remains? 6 minus 3, 3 nanoseconds. What is the next one? Next one is, I can continue from this side, P1. P1, again, I will write 3 nanoseconds, so 12, okay? And P1 execution time is 9, so 9 minus 3 is 6. So I will write it here, P1, with 6 nanoseconds. Then P4. P4 will be executed. Again, 3 nanoseconds. 15. And I will take P4, still 2 nanoseconds to go. P4, P4, 2 nanoseconds. Then P2. P2 will be executed. It is 18. So I will write here P2. P2 was 7. 7 minus 3 will be 4. Okay, we are close to finish. Now I will execute P5. P5 has 2 nanoseconds remaining, so I can't make 3 nanoseconds. So, okay, because of it is less than 3 for P5, I will execute it only 2 nanoseconds. So it is 20. Okay, because of it is remaining 2. It is less than 3. If it is more than 3, I will take only 3 nanoseconds. But if it is less than 3, I will take only that number. Okay, so P5 is finished. Then P3, 3 nanoseconds. So P3, 3 nanoseconds. So it is 23. This is finished again. So I'm not going to put it to the next. P1 is 6 nanoseconds left. So I'm going to write P1 6 nanoseconds, but I will execute only 3 of them. So 26. And here I have 3 remaining. P1, 3 nanoseconds remaining. The next one is P4. Again, it is 2 nanoseconds. So I will execute only 2 nanoseconds. So 26 plus 2, 28. P2 is 4 nanoseconds. P2, I will execute 3 of them. So it will be 31. So when I put it here back, I will put it here as P2. There is only 1 nanosecond left. So and the last one is P1 and P2 because P1 have 3 nanosecond left. I'm not going to put it because it is finished execution. Sorry. P1. So it will be 34. And the last one is P2. It will be 35. Okay. So the hardest part is to finish this one. The others are very easy. Here we are writing the completion time. Here we are writing turnaround time. And here writing average waiting time. I'm assuming that you know how to do it from the previous algorithms. Completion time is the completion time of each algorithm. So for the completion time, from the completion time here, because of each process is appearing more than once, I am advising you to start from the end and find the first appearance of each process from right side. So the completion time of process 2 is 35. Okay, it is finished 35. Completion time of process 1 is 34. This is, we did it. Completion time of process 4 is 28. Completion time of process 1, we did it. Completion time of process 3 is 23. Completion time of process 5 is 20. Why I started from the end? Because at the end, we can find the last appearance of the processes. Okay, so turnaround time is what? The arrival time, the completion time minus arrival time. Turnaround time is something like how much time you wasted. You go to a bank at 2 o'clock, waited 10 minutes, and your operation is 15 minutes. So total time you wasted in the bank is 25. So Turnaround time is 25. Okay. So completion time is the time that you finished. Arrival time is the time you started. So when you subtract completion time to arrival time, you can find the turnaround time. Okay. So it is 31 here, 30, 23 minus 2, 21, 28 minus 0 is 28 again, and 20 minus 1 is 19. Okay, and sorry, this should be waiting time, not average waiting time. Average waiting time is here. So waiting time is turnaround time minus burst time. Okay, so you think about that. You arrived to bank at 2 o'clock, waited 20 minutes. Your operation was 10 minutes. So at 2:30, you finished. So if you subtract 2:30 from, if you subtract the operation time from 2:30, you will find the waiting time, how much time you waited, something like that. So it is the turnaround time minus burst time. You can remember these things, or you can just by logically find it. Okay, so this is 22. 30 minus 7, this is 23. This is 21 minus 6, 15. This is 20. And this is 14. So to find the average waiting time, you have to add all these numbers. So I added all of them and divided to the number of processes, which is 5 here. Okay, so this is the answer. So if you the first procedure, if you can do the first procedure, the rest of them are very easy and same as the previous algorithms. Okay, I will continue from the next question because we wasted so much time. I am recording the lecture, so you can check it again if you need. Okay, in true false, by the way, I'm not going to ask true false questions. Just I will ask this kind of questions in the exam, but let me to answer them. A cooperative process is one that can affect the execution of another process. It is true because cooperative processes is something like one process produce something, the other one is consuming, or two processes may need some same memory element to do something. So it is true. The procedure involved in preserving the appropriate order of execution, cooperative process is known as synchronization. Yes, preserving the order of execution, synchronization, yes. To avoid race condition among the processes, we need to assure only one process at a time can execute within the critical section, which is called bounded waiting. Uh, bounded waiting. No, it is not bounded waiting. It is false. By the way, I didn't put the answer sheet with me. That's why. By the way, I'm not going to ask true false, but it is not bounded waiting. The critical section can be executed by more than one process at the same time. No, because it should be executed by only one process. So this is false again. When the deadlock extends to infinity, it leads to starvation. This sentence is just should be reversed to be correct. I mean, if when the starvation extends to infinity, it leads to deadlock. So this is also false. Okay. So I will continue. This next question is again related to the memory management. Link this, and it is very, very easy. Look, this is the memory illustration. I mean, this means how much memory it is taking. For example, let's say 0 to 199 megabytes or bytes, doesn't matter, okay? But this is shows the memory illustration. After compaction, they started to use linked list to more efficiently use the memory and also CPU as well. And by using linked list, they can just show which memory is in which location. I mean, which memory part is in which location, and they can easily separate the processes and empty places, and they can more efficiently use the memory, and also because of they don't need to just move continuously the memories from one place to another place, it will be more effective for the CPU usage. Okay, draw the linked list view. How we can draw it? We can do it like that, like a train. We can draw it like that, and if this is whole, write h 0 to 199. Okay, then the next one is process 200 to 499. It goes like that, okay? So if I ask you to link this view, you have to show it like this. If I ask you the memory illustration, you have to show it like this. So in the second question, I put it like that to this is part B. In the second part, it is saying draw memory illustration again if process 1 finish execution. So process 1 finish execution, let's say. So if process 1 finish execution, here we have whole. Okay, if holes I mean empty parts of the memory are one after the other. We are not separating them. Okay, we are separating them if there is one or more processes in between. Okay, so when this one is process one is cleared, this part is also a whole. So from here, from 0 to 599, it will be a big hole here. For processes, we are not doing like that because processes are different. So each process are different. Do not confuse that. I mean, process one, process two can be one after the other. But if holes are just like this uh, contiguous, we can think that it is a big hole. So draw memory illustration again. You will do it. Actually, I did it, but let me to do it again. Here you will write, let me to write process 2. Okay. Here it will be 600 to 899, this one. And this is from 0 to 599. Okay, it is a big hole. Okay. The questions was very easy actually, but you have to just familiar with them. Ah, okay, and the next question says, draw the linked list view of this. So it is very easy. Linked list view is just you have two different types. Uh, Here you have to put home. Here you have to say process or process 2 and write the numbers 0 to 599 and here 600 to 899. So this is the linked list view. This is the memory illustration. Okay. Okay. This part is the answer of part C. This one. Okay. The question is question 7. It is related to process life cycle. Uh, we did this in first, I mean, in the midterm, and I asked again. The questions was very easy here. Look, if a process P1 is in, let me to make it bigger. If a process P1 is in running state and another higher priority process P2 tries to enter the main memory, what happens to the first process? We have two scenarios here, in preemptive scheduling and non-preemptive scheduling. In preemptive, uh, when a process is executing by the CPU, when a process, let's say P1, CPU, and a higher priority process P2 enters to the memory. CPU will stop execution of the first process, I mean P1, and start to execute P2 because of its priority is higher than P1. Okay, in preemptive. But in non-preemptive, non-preemptive means if a process starts execution, if a process is executing by the CPU in non-preemptive scheduling, it cannot be interrupted by any kind of priority or this kind of thing, which means this process should finish execution. But do not confuse it with the input-output thing, okay? For both of them, process may need input-output operation and may go to do that task. But this is because of processes needed it, okay? Not because of higher priority process comes to the memory. Okay, so if in non-preemptive, if a process is executing by the CPU, it cannot be interrupted. So process one should finish execution, and after that, process two will be taken by the CPU. So this is the difference between preemptive and non-preemptive. And this is the answer of question one. I mean, the first part. By the way, I'm not hearing anything from you. I'm answering the questions, but I don't know if it is okay or not. I know that our lecture is solo, but I have to finish now.
So we are not seeing very well.
Sorry? You cannot see what?
Very well the answer.
I answered the question. You can see the screen? I don't get.
It's okay, it's okay.
Okay. So for the second one, let me to just take it to the same place. Explain when a process goes from suspend wait to suspend ready state. By the way, the answer is written here. If you write this, I will give points. Process completed input output, but still in suspend. Okay, so when a process is entering to the suspend wait state, when it is go to wait or block state because of it needs for input output operation, but uh, it is goes to suspend wait because of it is waiting for uh, input output, but also it is in a queue. So, by the way, and also memory is not available. So when it is going from suspend wait to suspend ready, suspend wait to suspend ready means, okay, when it is in suspend wait mode state, it can still finish its input output operation, but still memory is not available. So it is goes to suspend ready state, which means that, okay, I finished input output operation and I'm waiting for the memory availability. Okay, this is the answer of this question. Question 8. Uh, I ask you, write which line is entry section, exit section, and critical section of the fragment. Actually, after when it passes this part, it is goes to the entry section. When it passes to this one, it means it is in critical section. And when it passes to this one, it means it is exit section. But I'm not going to ask this kind of question, okay, in the recit. You are not, I mean, just I explained the question, but I'm not going to ask like question like 8. Okay, this is a kind of memorization question. The 4 criteria